All right, let's go. First thing, we just finished chapter 4, work energy. Today we're moving on. Next 2 weeks we'll talk momentum. Those are the two things that are going to be covered on your second exam, which is 2 weeks from yesterday. So on Canvas, there will be a midterm 2 module. It'll show you the time and the place. Those of you guys who have a conflict, there's a little request for an alternate exam time. So go check that out. Figure out what you got going Monday, November 8th. And then please, if you need an alternate time slot, let me know. Okay? All right. So that out of the way. So chapter 4, what do we do? We took F equals MA. We integrated this thing along path, right? So we started with Newton's second law, integrated it over the path, and we got something that looked like kinetic energy plus potential energy plus the work between the two states is equal to the kinetic energy at state 2 plus the potential energy at state 2. Right? This work, we said, was from the non-conservative forces because we pulled out work done, V1. We pulled out the work done by the conservative forces, namely gravity and spring forces. But really, we talked about this being kind of a shortcut for problems that dealt with speed and position. If I asked you specifically for forces or accelerations, maybe this isn't the best thing to use. But problems with speed and position, this was the quick way to do it. So now we're moving on to momentum. Well, we're going to start with the same thing. F is equal to ma. But this time, instead of integrating with respect to the path, we're going to integrate with respect to time. So we can say that acceleration is dv dt. And then I can rearrange this. I can get my force dt is equal to mass dv. Integrate both sides of this. So on my my left-hand side, I've got force integrated with respect to time. We're going to call this our impulse. And we'll usually use I for that. And give myself a little more space. It's a vector quantity. So if you think about what we had last time in chapter 4, our work was force integrated with displacement, but that was two vectors with a dot product. So poof, the vector part went away and we left with the scalar, right? This case, we're just integrating force with respect to time, so we're going to be left with a vector. So the integral of a derivative, if I call this, I'm integrating from v1 to v2, this side just becomes m v2 minus m v1. So a little bit of rearranging now. I've got impulse is equal to mv2 minus mv1. Give this the old switcheroo. Move the v1 to the other side. So I got mv1 plus some impulse is equal to m massive times velocity at 2. Hey, we've got a nice state equation just like we had last time. So for work energy, we said, hey, how fast are we going kinetic energy at state 1? We got kind of something similar for momentum now. What's my momentum? Mass times velocity at state 1. Here I've got potential energy term. That doesn't really exist for momentum. But then I've got the work done between states 1 and 2. Well, the work is kind of my analog to my impulse. Instead of force integrated with respect to its displacement, now we've got force integrated with respect to time. It's equal to mass times our velocity, SA2. So we call this momentum impulse, the momentum impulse principle. We've got momentum, this mv, sometimes we'll call that p. So p1 is mv1. So we could rewrite that. I'm sure I rewrite that somewhere. P1 plus my impulse is equal to P2. Maybe think about what we have here for a particle. And this is state 1. It's got some velocity. It's going this way. And this is my V1. And it's a vector equation. I'm going to apply some impulse to this. So my impulse, what? That's just forces integrated with respect to time. So maybe I've got F1 working on it, F2, F3, who knows? Whatever you want to put on there. I've got a bunch of different forces. That's what's going to make up this impulse. So my impulse looks fancy, but it's just the integral of those external forces. So I'll say I equals 1 to n, however many we have, integrated with respect to time, from state 1 to state 2, or time 1 to time 2. So if we think of work energy as a shortcut, again, for speed in position, now when I take a look at momentum, this, remember, our momentum is m times velocity. These are good for problems with velocity and time now. Just think with work, we integrated with respect to position, but now with momentum, we're integrating with respect to time. And I did something a little sneaky in here. I said for work, it's a shortcut for speed. There's one thing we care about for work energy is we have a scalar equation. So half mv squared. I don't care what direction v is pointing. I just need to know v, right? So scalars, no vector, no direction. I don't care. So I can call it speed. For momentum, now I call it velocity. Velocity, when I say that, I mean I need a speed and a direction. This is a vector equation. So maybe what I've got here for this problem, maybe I've got an xy system. And I'm actually writing an equation for x and an equation for y. Right? I have maybe my x equation here. So what's my initial momentum in the x direction plus my x impulse equal to my, well, I guess I don't need vectors. Maybe I could do this. Instead of the vector, call that the I direction. And my impulse in the I direction is equal to my momentum SA2 in the I direction. And I could also have the same thing for y. So I think the number one thing people mess up with these problems is you get so used to writing just the state. Like, hey, T1 V1 plus U1 is equal to T2 V2. Okay, and then now you get to momentum, and you write that same thing real fast, and you forget that it's a vector quantity. So now we have, really, if you want to think of it this way, we have like an extra piece of information buried in there, right? Because we know what's happening in one direction and what's happening orthogonal to that in the other direction. And if I was really mean and this was a class where we did 3D, we could have an out of plane direction too, right? But for us, we're just worried about 2D for now. This figure on the screen here, what it's showing us for impulse, it's the integral of force with respect to time. So maybe a nice way to think of that or to visualize it, I've got time. I've got force as a function of time. Maybe that goes like this. And if I want the impulse between, say, time 1 and time 2, it's the integral of force with respect to time over those values. So what's the integral? Area under the curve, right? So that can help us visualize what are we talking about here? Oh yeah, this integral is just what's happening, force over that time. Try not to make it too complicated. So this slide is what I've been harping on the whole time. Hey, impulse momentum, that's what we're doing now. It's just like what we did last 2 weeks for work energy. Except, now instead of a scalar equation, we have a vector equation. So that's going to be the main difference that we'll play with today. And again, work energy, speed and position. So when you take this next exam, you're like, oh, I don't know which one to use. Well, do I give you information about how fast it's going and then like where it is? Maybe compressing a spring or at the top of a hill. Hey, that's speed and position. If I give you something about velocity and time, that's momentum impulse. So being able to separate these two. And sometimes the two problems can work together. So I might use work energy to start the problem and momentum to finish it, or vice versa. All right, so let's talk about this idea of average force when we're looking at impulse. So we've got our ball at state 1 again. And it's traveling with some velocity. I'm applying some force to it. And you think what we do. All right, if I'm doing impulse momentum, I've got the mass of this ball multiplied by its velocity plus the integral of this force with respect to time between states 1 and state 2. If I knew what this looked like, if this force as a function of time was like that, we would simply integrate over our T1 to our T2. Maybe it's some easy function. Maybe it's a graph. Maybe you can put it together. So if I had these two, we could get what's happening at state 2. So given our initial velocity, given a well-defined force, I can tell you how fast something's going. Okay, that's like the baseline. Problem is, it's not always easy to do that in reality. So the example that I like is baseball. I've got a bat, and I've got this ball coming in, right? So for the time being, this ball is coming in hot. Pitcher threw it. It's going to hit this bat. There's going to be all sorts of crazy forces happening. F of t time. Now, when a ball is going to hit a bat, you're probably going to see some like massive force, right? And it's going to be for a short period of time, and then it's going to die off. But maybe it's easy to put your radar gun on and see how fast is the pitcher throwing the ball. And maybe it's easy to keep that radar gun and see how fast the ball is going afterwards. But actually figuring out, going in there and saying, well, what's the precise force that's happening during this time is hard to explain. It's hard to quantify, or it's hard to measure that force that's happening over, like 0.005 seconds. This impulse is very, very short. So maybe you know this stuff. You know what the ball looked like coming in, and you know what the ball looks like going out. You want to try to figure something out about this force. Maybe you got a super fancy slow-mo camera, and you put it on there, 500,000 frames a second. You can tell that the ball is being squished against the bat for some amount of time. Okay, can I figure out the force, right? That's the gotcha here. So think about what we know. I've got velocity, and remember, it's kind of coming in this way, plus I've got the integral from states 1 to 2 of this bat force, dt, and then I've got my ball flying in the other direction. I can move this to the other side. That's a 1. So I could tell you, just based on how fast the ball's leaving, how fast the ball was coming in, assuming they're in opposite directions now, I could tell you what our impulse was, right? I could say, hey, this is how many force over seconds, so Newton seconds, of impulse that I had to switch this ball's speed. But if I wanted to tell you what the peak force was, I don't have enough information to do that, right? If we had our super awesome camera, we could tell you that contact was being made for 5,000ths of a second, or 5 milliseconds. And we could go in here, though, and get an estimate for what the average force is. So average force might look like something like this. We don't have a good description of what the exact force was, but the area under the curve for our average force over our time interval will be the same as the area under the curve for this blue guy. I'm just doing some coloring. Right? So sometimes we use this idea of average force acting on the system, well, one, because this is hard to get without some very, 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 very fancy measurements. Sometimes that's good enough. That's all we need, is to know. If this is what the impulse is, this is what our velocities would be like before and after. So this idea then, if we're using an average force, that integral is a constant, right? Our force is a constant with respect to time, so I've just got average force times our time interval. Because really, instead of doing an integral of the area under this curve, I'm just doing a multiplication of this rectangle. This is my average force. That's the time it's happening. Sometimes that's all we can get. All right. Let's put this to work. So here we've got a fuel element assembly of a nuclear reactor. It has a weight of 600 pounds, suspended in a vertical position, initially at rest, okay. And we're given an upward speed of 5 feet per second in 0.3 seconds using a crane. Determine the average tension in the cables during this time. All right, so the first thing I start doing when I start looking at these problems is, what kind of info am I given? given something about speed, feet per second, given something about time. And it's happening over 0.3 second window. So, hey, I want to figure out the average force that's happening in this. So I've got W working down. I got a pair of these tensions to deal with. Those tensions are what I'm trying to figure out. So the free body diagram for us, W down. I've got this angle theta for each of these guys. Tension working up. We're given that our weight is 600 pounds. Oh, I saw someone on Piazza throw out the question, how do I know if it's pounds force or pounds mass when you give it? It's pounds force. We're always working, whenever we say pounds, it's pounds force. Pounds mass is like a goofy made-up unit, right? English units for mass are slugs, unfortunately, or slinches. So if we got weight in pounds force, to get mass, we had to divide by gravity. That's kind of our... And if we divide by gravity as 32.2 feet per second squared, feet, then we get slugs. If we divide by inches per second squared, then we get slinches, which is not something we want to do, okay? So we're given our weight. Sorry, I just remembered I saw that. Our initial velocity was 0. We're starting from rest. Our final velocity, I'm going to write this as a vector actually, was 5 feet per second in the positive j direction. We're going up. And my time, my delta t, 0.3 seconds. We're trying to find our average tension. All right. So again, problem dealing with position in time, trying to find an average force. We're going to use some momentum here. So momentum, impulse, or impulse, momentum, I just flipped them. I've got m, my initial velocity, plus my impulse equal to mass times my final velocity. For us, we're at rest. Our initial velocity is 0. Our impulse is the integral of the force dotted with time, right? We know that we're just looking for the average, though. So we're not trying to fully specify our force because we got this guy. We're just looking for the average force. So again, that's going to be a constant value. So this is really going to be force times delta t, right? Because this is going to be a constant for our average force. That says constant. All right. So to do this, our free body diagram is going to help us. So our impulse is the sum of all these external forces. So what is our force? Here, our direction that I'm interested in is the y direction, because that's where we're pulling up. I do have impulsive forces in the x. T's got some, and this T's got the opposite. But you can imagine one plus the other, they're going to go to 0. So for us, we can look at the y direction. So the forces I'm interested in, I'm going to look at forces in the y. This is going to give me minus W plus the contribution from each rope plus 2t, and I only want the cosine leg of these, 2t cos theta. That's my external force in the y direction. So now my momentum equation for the y direction is this guy. The impulse side, 2t cos theta minus W times delta T is equal to mv2 in the y direction. Most of this info we have. So my mass, 600 pounds over 32.2 feet per second squared. Let's go from a weight to a mass. So that's a check. My V2y, that is positive 5 feet per second. It's going up. My W I've got. My theta I've got at 30 degrees. So I can solve this for tension. It's the only variable left. And my delta T is 0.3 seconds. So plugging in, solving for T, 526 pounds. And I'm going to sneak in average, AVE. Right? So over this 0.3 seconds, that tension as a function of time, phew, it might look like that. Maybe it dies off like this and it's more constant. But we're just finding F average or T average. We don't know exactly the shape there. We're just trying our best to approximate it with our average force. Okay, so leveling up in one level of difficulty now. So we've got momentum, impulse. If I know what my particle is doing, I do something to it for a given time, then I can figure out what my particle is doing afterwards, right? Momentum, impulse. If I got a system of particles, maybe they're doing all sorts of funny stuff. Maybe they're banging into each other, which is what we'll talk about next time with impact. Call that A, call that B. These guys are heading right for one another, right? They're going to come together, and then when they smash into each other, there's going to be some normal force between them, right? Maybe I've also got an external force on A. And maybe I got an external force on B. Well, for our momentum, we can do momentum of the full system now, as opposed to just looking at one of these particles independently. So when we do this, our equation is going to look really similar. We're going to have the sum of our momentum at state 1, I equals 1 to n particles, plus our impulses. We got the sum over I equals 1 to n particles, the integral of all these forces, dt, is equal to our momentum at state 2. Looks really similar. This problem, the way I've drawn it up, the point we're doing is we want to make sense of what's happening from these internal forces. Hey, if there's external forces on the system, they're going to affect our momentum. I better take care of this FA and FB. But if you think of what I'm doing here for our normal forces, if I'm integrating that force over time, I take the contribution from B onto A, and I integrate that with respect to time, NAB pointing to the left. And then I look at the opposite force, NAB pointing to the right, the force of A acting on B. Hey, equal and opposite. if the force is equal and opposite, and they're operating over the same time because that's the contact force, the integral, or the impulse from any internal forces is going to go away. So life gets a little easier for us. If I've got a system, I don't care what's happening on the inside. I can just ignore. And I just have to keep an eye on those external forces when I'm operating over a system. If you're lucky enough, maybe you have no external forces. You've just got these two things smashing into one another. I don't know why I drew it that way, A and B. So when these guys crash into one another, yeah, we got normal force, but they're going to cancel. So, no external forces, this part falls out. We've got no impulse if we've got no external forces. Even though crazy stuff is happening, these two things are colliding, I got no external forces, so my momentum is conserved for the system. So we got no external forces, we call this conservation of momentum. So conservation of momentum, simple. The sum of my momentum at state 1 is equal to the sum of my momentum at state 2 over all these particles. If you don't like it this way, mi pi1, I equals 1 to n, sum mi pi2. I want P in there. Sorry. Pretend I didn't write that. I wanted velocity. So my mass times my velocity at state 1 equal to the same thing at state 2. My mass of the individual particles dotted with my velocity of those particles multiplied by at state 2. We hope life is this easy. This is one thing we don't have to worry about then. For us, to keep in mind though, still a vector equation. So we might even have this. We might have conservation of momentum in one direction but not the other. So, hey, these two particles are flying at each other, about to collide. And then I also threw in an FA. Oh, I've got conservation of momentum in the x direction, because this is a vector equation, but I don't have conservation of momentum in the y direction, because A is got some external force we have to deal with. So, conservation of momentum, again, vectors, so we got to think about splitting it up into both x and y cases. I just said all this stuff. All right, here's an example that can help our intuition. I got these trains. They're cruising on the track, and they're going to collide. I just drew that picture, right? I just drew a picture of a ball, another ball, smashing into one another. And I said momentum was conserved there, because I have no external forces other than what's happening between these two trains. But what we'll show in this problem is that this has got conservation of momentum. The only internal force you're going to get here is this NAB. Well, that's an N. But this does not imply conservation of energy. So just because we have conservation of momentum doesn't mean we have conservation of energy. So we'll do a problem here where there is energy loss. You can imagine, I take one train, big and heavy, I smash it into another train. Yeah, momentum might be conserved, what direction they're going to move in the end, but there's going to be tons of energy loss, right? Energy loss through heat and friction and exploding things. So that's what we'll do. So for this one, I've got train A. We're moving on a track So really, I just care about the x direction here. We know momentum is going to be x and y, but for this case, we're just smashing into each other like this. So the mass of A is 15 megagrams. That's interesting. 15,000 kilograms. And it is coasting at 1.5 meters per second on a frictionless track in this direction it's shown. So 1.5 meters per second. So my velocity of A at state 1, 1.5 meters per second in the I. At the same time, car B, which has a mass of 1,200 megagrams, or 12,000 kilograms, is going the other direction at a speed of 0.75. So my initial velocity of B is minus 0.75 meters per second in the I direction. It's going the wrong way. This is where people will screw up and they're like, you kind of forget the fact that I need the vector here, so this one's 1.5, this one's minus, because it's going the opposite direction. So they're going to go the opposite direction. When the cars smash together, they get coupled. So they get entangled. And we want to figure out the speed of both the cars just after impact. So when they get smashed together at state 2, the velocity of A2 is going to be equal to the velocity of B2. So they're just going to get totally smushed. We want to find the velocity of the cars after, and the change in energy, or the work that was being done between these two states. All right, so to begin, the only force we're going to see here is internal. Part of the problem that maybe we didn't pick up on, these trains are coasting. If they weren't coasting and they were still motoring, they would be applying a force over this time interval that they're smashing together. That force that they were applying, that would be an external force. We'd have to count for that. But since it says coasting, we can just assume that these guys are rolling towards one another with their engines shut off. So if we use momentum, this is conservation of momentum. We've got, here I'm just going to jump to the x direction because that's what we're traveling in. So I've got P1x plus P2x plus an impulse, which we already said was 0 because we have all internal forces. It's equal to, oh man, I'm changing my notation, sorry. I called this 1, and I wanted this to be A and B. So PA x of 1, sorry, PBx of 1. So the momentum of train A in the x direction at time 1. The momentum of train B in the x direction at time 1. Equal to the momentum of train A in the x direction at time 2 plus the momentum of train B in the x direction at time 2. All right. Momentum is just mass times velocity. So I've got MA VA1 plus MB VB1, which we've got written out, is equal to, these guys are moving at the same speed. So I'm going to do a little switcheroo. If I know they're both going at V2, And I'm going to drop the A and B subscript because I'm just going to call this 2 because they're coupled together. But I've got the mass of A plus the mass of B at state 2. So if we plug in, we got a mass of A, we got a mass of B. This velocity of A is 1.5. My velocity of B minus 0.75. V2, 0.5 meters per second. And I'm going to give this some direction. Positive in the I direction. So the fact that when these things smash together, they keep moving to the right matches intuition, at least, because car A was heavier than car B, 1,500 kilograms versus 1,200 or 12,000 kilograms, and it's moving faster. So I've got heavier and faster smashing into lighter and slower. They get tangled together. You can imagine they're still going to be moving in that direction of heavier and faster. So overall, conservation of momentum can get us to what that speed is. Second part's energy, though. This is taking us back a week. T1 plus the work between states 1 and 2 is T2. So we want to see what kind of work was done in that crash. So the work between 1 and 2 is T2 minus T1. So the amount of work, T2, half mv squared. ma plus mb, v2 squared. I lump these guys together because they're stuck together at state 2. Minus what's happening at state 1. They're not stuck together at state 1, so I got to account for their velocities individually. Half mass A, VA1 squared, plus half MB, VB1 squared. Hey, velocity squared. These velocities I can handle like speeds now, right? I don't care if it's going left. I don't care if it's going right. I just want to know about the energy in the system, what it contains. So this (20.25 kilojoules). This, after our impact, this is kind of before. This is after. After, you expect a lot less energy, right? Because during that impact, we burnt up a lot of work. We had plastic deformation of these two cars as they smash together and crumple. So this is only 3.375 kilojoules. So we lost about 85% of our energy from smashing these two guys together and having them get stuck. But we had conservation of momentum. So this is trying to just display conservation of momentum, conservation of energy, two separate things. We don't need to think one is the same as the other, or if one, then the other. Last one. We got a toboggan going down the hill. Boy and a girl riding a toboggan. Toboggan weighs 10 or has a mass of 10 kilograms, starts from rest. Girl and the boy, 40 kilograms and 45 kilograms respectively. When the toboggan reaches the bottom of the hill, the boy is pushed off the back with a horizontal velocity of 2 meters per second of the velocity of the boy relative to the toboggan. Classic. Ladies always pushing us off. Determine the velocity of the toboggan after he's kicked off. Neglect friction. So what do I got here? I've got this system. This is kind of a problem that's trying to bring us back to a little bit of what we did before. I got some hill. I've got some idea that I started from rest. So V0 is 0. At the top of the hill. What's going to happen? These guys are going to go down the hill together. Life is good. When we get to the bottom, pew, we're going to kick this guy out, right? So, starting this problem, we can do work energy. I'll call this state 0 up here. State 1, they're all riding the sled together. Everyone's happy still. And state 2, there's a better sled. This guy is getting chucked off the back. So we can do work energy to get us from the top of the hill to the bottom of the hill. Everybody's together, riding in harmony. All we're doing is potential energy term, trading that for velocity. I think that's super easy. So I'm going to say that our velocity, I'm just going to give us that, 7.67 meters per second. And this is in the minus I direction. I'm going to pick a traditional XY. We want to know how fast we're going at the end of this. So velocity of the toboggan at state 2. Is what we're trying to figure out. And we know that the velocity of the boy relative to the toboggan is 2 meters per second. So we don't know how fast he's going, but we know how fast he's going relative to where he just got kicked off of. So think about what's happening here. You can draw a pretty fancy free body diagram if we're neglecting friction on the bottom of our toboggan. This girl pushing this guy, these guys sitting on this sled, all those forces are internal. So the only thing that this system sees on the outside is, I guess, nothing, right? We don't have any resistance from air. We don't have any friction from the hill. All the forces are internal. So again, this looks kind of complicated, but it really is going to be another conservation of momentum problem, where there are internal forces from this violent push, but we don't have to worry about those because they're internal, equal and opposite when they integrate. So, conservation of momentum. So what's happening at state 1 is what's happening, momentum-wise, at state 2. So, write it out. At state 1, we're all going together. We're one happy family still. So I got the mass of the toboggan, the mass of the girl, the mass of the boy. We could have done those separately. And they're all going at V1 in the I direction. V1 happens to be minus 6.76. Then, the girl and toboggan stay together. So the mass of the toboggan plus the mass of the girl times the velocity of the toboggan at state 2 plus what the boy's doing. The mass of the boy times the velocity of the boy at state 2. And you think, I've almost got enough to solve this. But we're not given the velocity of the boy. We're given the velocity of the boy relative to the toboggan. So we have to do a relative velocity. I can write the velocity of the boy as the velocity of the toboggan and the velocity of the boy relative to the toboggan. So to get VB2, I can say this is equal to the velocity of the toboggan at state 2 plus the velocity of the boy relative to the toboggan, I guess at state 2. Velocity of the toboggan is what we want. We're given the velocity of the boy relative to the toboggan, and then we would have the velocity of the toboggan in both sides, or in both these terms, as our only unknown. Okay, I'm out of time. I will beautify this and then post it for you.